Hello students, welcome to the class of Digital Signal Processing. And today we are going to deal with a very interesting topic called the Fourier analysis. This topic is given as discrete Fourier transform in your syllabus of PC 801 from Macau's West Bengal. But we will be studying it from the very beginning, that is from Fourier analysis. Fourier analysis is rightly called the unsung hero behind countless technologies. Whatever you see around you, like uh, images from in a computer, mobile phones, live streaming, and people talking from space to someone on Earth. There are different types of communication that is possible. The how the devices are interconnecting with each other. All these things have been happening because of the very important mathematical tool that is the Fourier analysis. So you need to really appreciate this mathematics behind this, all these technologies, and that is the Fourier analysis. From the music we hear to the images that we see, universe often speaks to us in the form of waves. Once you delve into this Fourier analysis, you will find that any signal, any type of signal that you see in the that you encounter with, that is in the physical world that you create, all can be broken into sums of sines and cosines. And that is the very basic from where the Fourier analysis started. So first, we need to understand that universe often speaks to us in the form of waves. We have also studied about wave-particle duality. So whatever you see as a particle can be transformed into wave, and whatever you see as wave can be transformed into particle on a very big scale when you say, or you can say if you see it on a minute scale, both ways you can say it. So these are all just philosophy, but yes, the Fourier analysis is a mathematical tool which is extensively used in signal processing and systems theory. It helps us to investigate the relation between time and frequency domain. So we have already talked about time domain. We have also talked somewhat about the frequency domain in our communication classes. Basically, when you see the signal, how the signal is changing with time, that is the time domain analysis, it reveals the shape of the signal. And when you see how the signal changes with the frequency, that is the frequency domain analysis. But here, the major thing that is coming in is that frequencies that are present, the relevant frequencies are lesser in number, but the time you have to see for the whole duration, but the frequencies are, there are selective frequencies which have significant magnitude to be studied. And that is the usefulness, you can say, for the Fourier transform. Or you can say that that is the usefulness when you see the signal in the frequency domain. What is signal processing? Is transferring a signal from one instrument to other, or from one component in the instrument to the other component, or you can say one device in one place to the device in the other place. That is, you can say from one point of the world to the other point. But basically, the processing, the passing, or you say that transferring of the signal happens between two devices or two components, right? And then the systems theory. Systems theory is basically when you change the input, how the system is going to react, or how is the what is the limit of the system, or in very short, you can say whatever you studied in your control system classes that comes under the systems theory. So these two are the major backbone of engineering today, and this has been, you can say, the major backbone of electrical engineering today, and this has been the possible because of the Fourier analysis. Let's go next. Here you see an orchestra where people are sitting with different musical instruments. So a particular sound is coming out after they play it. And when you break those sounds into its constituents, or if you want to analyze how each instrument is, which at which frequency each instrument is playing, so that is the Fourier analysis. The whole sound is coming to you, and you want to divide the different frequency components of that sound. Then you say that you are doing the frequency analysis. That means decomposing a sound into its tones. That is your frequency analysis. Made more better in a more better way you can, or in a more simpler way you can say, you will be able to understand with the help of this example, where a white light is passing through a prism and getting splitted into the 7 colors of the rainbow. So the prism over here, it is acting like a Fourier analysis tool. Why? Because dissociating this white light, or it is separating the white light into its constituent colors. So all the colors have a particular frequency which were combined into the white light. And now with the help of the prism, you can see the components and you can see the contribution of these signals to the white light. The same way the thing was over here when the particular music is coming and you are analyzing that music with which frequency is contributing how much to the music. Another, the very things that I was talking in the very beginning was about the communication system. You can see a cell phone tower is there, and that cell phone tower, because of that, the places are getting connected. Because of that, the communication is possible. Your voice, whatever you speak, that is getting transferred at different frequencies to the person whom you want to speak with or to the device. So that is the way at a single time you have you have transferred the voice with different frequencies at the same time. So that helps us in communication in a more better way. You can understand with the help of a radio, where you have different channels, all are playing their events. They are booked for different events. So what they do, that if you can also see that at the same time events are present in every channel. So how can you access them by tuning into the particular frequency. Suppose you want to hear to a particular music which is being played at say 500 or some hertz. So then you need to tune it to that hertz, and then you need to hear it. So that is the way how you select the frequency and you can hear it. So this has been possible because the different components of the frequency has been differentiated, and that has been possible because of your Fourier analysis. Of course, when any great discovery takes place, there has been a lot of work behind this, right? So, and this great work has been the contribution of brilliant minds. And like any other scientific discovery, it is not the work of a just single mind not just a single person or a single mind, but it has been over centuries, constellation of brilliant minds who have contributed to this grand scientific epic. And this story we will be dealing with today, so that you get inspired to contribute, and also to appreciate the contribution of these people in the Fourier analysis. So first of all, the center one, Joseph Fourier. He was the one who said that any function can be represented as a sum of sine and cosine. And this was a very bold and radical idea at that time, which laid the foundation for the new era of mathematical analysis. What he said was that any function, mark my point, any function can be represented as sum of sines and cosines. And before Fourier, there was Leonhard Euler, who was a very, very, you can say, mathematical titan. What he did was he has contributions in every area of mathematics, but his work on infinite series, particularly on trigonometric series, laid the groundwork for Fourier analysis. He developed the exponential form of complex numbers. So he developed the exponential form of complex numbers. Now this laid the foundation for Fourier analysis. This we will be studying in detail in this class itself. Basically, what he did, that he gave a vocabulary which is needed to describe oscillations. What Fourier did was he had given the statement that any function, any periodic function, any periodic function can be represented as sum of sines and cosines. And later you will find that any functions. So that was the contribution of someone else. We will be coming to him. So this was it. Now, Leonhard Euler, you have understood that what he did was trigonometric series. He was studying infinite series, where his contribution to trigonometric series laid the groundwork for Fourier breakthrough. What he did was he developed the exponential form of complex numbers. So what was that? Cos theta plus j sine theta. What you write it as is equal to e to the power j theta. And that means cos and sine can be represented as e to the power j theta. So yeah, just keep this in mind. We will be dealing with this again. Now, the person called Duhamel, J. Duhamel, what was his contribution to the Fourier analysis? He was studying heat conduction. So uh, he explained how heat spreads to an object with irregular shapes and varying temperature. The heat is how it is spreading to an object with irregular shapes and the varied temperature. So he tried to develop a model for that, and that while while using partial differential equation, he also got the usage of Fourier analysis to solve partial differential equation. And this was a very, very big thing, because any model you make, any physical model you make, that can be represented by a partial differential equation. And when you can represent that partial differential equation, or you can solve that partial differential equation with the help of Fourier analysis, then of course the importance of Fourier analysis becomes manifold, right? Then comes PGLD Dirichlet. Now this person, what he did was very, very important. Like, what he did was to tell you the limit of the Fourier series. So he wrote the conditions for the convergence of the Fourier series, how the Fourier series can become equal to the exact function. That was his contribution to the Fourier analysis. In simpler term, you can understand that you're building a bridge, suppose, and you don't know how much cement you need to put to build that bridge. How much? What is the limit of that cement? So that is the work. He put the limit. That is he has given the framework for Fourier analysis. He gave a stability to the Fourier analysis. So that was his contribution to the Fourier analysis. And then came Riemann. He has tried to advance the theory of integration, which was necessary for Fourier analysis. So what he did was he measured the area of shapes with infinite complex boundaries. So with simple area of rectangle, square you measure. We have also studied about integration, where we can measure the uh, area of irregular shapes, but infinitely complex boundaries. And so he contributed to the theory of integration, which was later used in Fourier analysis. And when this then comes Henry Lebesgue, he introduced integration and refined integration for the Fourier analysis by including the set theoretic aspect of it. This was his contribution. So basically, Riemann and Lebesgue has contributed to the integration part of the Fourier analysis. And then comes Norbert Wiener. What he did was bridging mathematics to engineering. So he developed Fourier transform. So till now we had the Fourier series, right? And Norbert Wiener, he developed the Fourier transform theory, where he included all the signals. Till now it was just the periodic signals, but now the non-periodic signals can also be analyzed using the Fourier transform. This was his contribution, which had to go a very, very long way, because he bridged the mathematics to engineering. And also you can say that he has tried to convert the abstract world of Fourier analysis to the practical application of signal processing, because he has been able to analyze that not only repeating patterns but also non-repeating patterns can be analyzed with the help of Fourier analysis. So this is the contribution of these 7 great minds to the Fourier analysis. Now from here, what we understand is that oscillations are present everywhere. Oscillation, what is the meaning of oscillations? Means you're starting from one point and coming to that point again. So a circle can be represented as an oscillatory motion. Okay, now, so in a big sense, I'm telling. So any sustainable dynamic system exhibit oscillatory behavior. Things that do not move in a circle do not last. So that is a very, very important, and also you can say a philosophical thing. Because say you have you can say a bomb. Okay, the bomb is having great energy, but once it bursts, it has nothing. Then it cannot come up again. Same the case with a human being also, right? So that things which do not move in a circle, that do not last. basically here the idea that I want to give is that sustainable dynamic systems. Now, sustainable dynamic system means that the system which is able to which is able to hold its energy, or okay, you can say that which is able to perform some kind of oscillatory behavior, are able to sustain in the world. Okay, so after this, let's see the pictures over here. The heartbeat, then you have this musical instrument and the waves. All these are can be represented with the help of oscillation. Now, any signal that you have, any function that you have, that can be written as a sum of sine and cosine. So the green color you see over here, it is the sine wave, and the blue one is the cosine wave, right? So when you combine these two, the sine and the cosine part of it, then you can understand that the sine and the cosine part together, if you combine it and write it into one part, you can write it as e to the power j omega t. So this was the contribution of Euler. He said that e to the power j omega t is equal to cos omega t plus j sine omega t. If you take a point over here, this black point over here, the particle is starting from this point and coming back to this point. So this motion can be represented as sum of sine and cosine. Okay, so this side, when it is going on the real axis, if we take this one as the real axis and this one as the imaginary axis, then what we have, that this portion will be represented as the cos part and this as the sine part. And when you actually want to have this value, this position, you go on horizontally and then vertically. So every motion can be represented as this type. In this, every function can be represented as a sum of sine and cosine, and then you can again represent it as exponential form. Okay, why we are using complex exponential when we already had this system, that the system that we are having cos omega t and sine omega t, then why do we need to make it e to the power j omega t? So this is the thing, that it can be used in digital systems. First thing is that it can be used in digital systems, and every sinusoid can be written in terms of sines and cosine. Very, very important thing is that trigonometry becomes algebra. This is a very important thing. And one more thing that you need to understand over here is, see, complex exponential. Let us go through this portion of it in a more better way. I think I'll have to share this. Okay, let's do this part in the next class, where I will be teaching you why we are using this portion, how we are using this portion e to the power j omega t as the sum of the sine and cosine, and then also why we are representing this oscillations in this manner. Okay, so we'll start from this slide once again so that there is no breakage. Okay, thank you everyone. Let's meet in the next class.